Alrighty then, hit the button and such. We'll change the chat, pop out the chat, this little crap done, and such. Alright, so I do intend to explain this. Yeah, there it is on the screen. And this is all there is in the universe, okay, is, yeah, these big things come in two forms and a bunch of little things that are in two forms. And just the interactions between them are pretty much just two. So it's pretty much just 2 plus 2 plus 2 is a whatever. Kind of a joke. But anyway, first, okay, just briefly, yeah, just bizarrely, there is this weird comment by the Brozo, and who knows what it means? I don't know, it's some kind of joke. So it says, "Catch you later, Michael." Okay, I still haven't dropped into that 220,000 pounds. So where he came across that, the other day he was searching through his money to buy a little more electricity. So I don't know. My sisters think I'm joking about probably donating it to a cat rescue organization. So this just proves how depraved and sick this little fucker is. I mean, he's not, there's no association like he's ever had a cat, like he even knows what cats are. And it's just because this has been raised by some people as an issue because, I'm not for rescuing cats if rescuing means let's do a bunch of surgery on them and then throw them back into hell. That's not, in my opinion, rescuing something. Okay, that's not my definition of a rescue. If somebody just takes me out of my house, cuts my nuts off, and then throws me back in the same place I was, no, I don't want that rescue. Thank you. It's just a veterinary, get rich scheme, frankly. I mean, all people are doing is making vets rich, paying, exorbitant fees for minor health care for cats. So yeah, if you want to throw your money away, this is the way to do it, in my opinion. So this is why he brought it up. He didn't bring it up for any other reason. So his sister, my sister, so he actually said this to his sisters, like he's going to donate the money to a cat rescue organization. Again, just shows how psychotic he is. This wouldn't occur to him before he knew me. Oh, it's just so funny. I might buy a proper high-speed camera. Yeah. This is what occurs to him. So $220,000 falls in his lap somehow. I don't know through what mechanism. And this is as imaginative as he is. But I have no real use for one. So he can't really imagine how he could do much better experiments with a high-speed camera or even a stroboscope. Okay, the GoPro does me fine. It doesn't do the rest of us very fine. I can't even be bothered with a new PC because of the hassle of installing software again. Maybe you could hire somebody to do that for you. Oh well, I may just roll dice. I mean, this is how, whatever. Oh, that's just so brilliant. Ha ha. Alright, if I had it when I was younger, I would have spent on women. So I guess he's just, I think you get what I am saying. So what, he would have bought prostitutes. Or he would have convinced some scientific woman, to abandon her scientific pursuits. He would have bribed some woman. I mean, just, I don't know. Just, what a piece of shit. The world is a sick and horrible place. Anyway, alright, so back to the real video. So I just thought I'd go over some of this stuff that I haven't been over in a while, so I might as well make another video about it. And I've sort of soiled it with the Brozo crap, but that's okay. Yeah, nothing's perfectly clean in this universe. This world. Alright, so if I get rid of that, no, that's not what I want to get rid of. Get rid of this. Yeah, get rid of the other one. This thing's in the way. Okay, so I have to get rid of that. So you saw that, right? You get it. I don't have to explain it again, right? Jesus, nothing. Come on, I want to move this thing. All right. So the simulation works really simply, and so I explain the idea. So this started with arguments about gravity, and the fact is that I found the idea of bent space to be kind of silly, and so I went looking to see if I could figure out some way to make it out of a real force. And in my opinion, I did, sort of, okay, in the sense that you can make a particle model work, but the trick is this idea that it creates drag. Why can't I find the thing I'm looking for here? Select the right box, please. Where the hell is it? I guess it's way over here. This is a minor improvement, frankly. Yeah, it really wasn't worth all that time. All right. And yeah, I didn't really deal with the drag problem as well as I should have, frankly. And now I think I have a much better explanation. But regardless, that's sort of where it started. And then it got to the two slit stuff. And that's where I really started saying that the whole model of physics is broken. And so, yeah, I tried all kinds of ways to make waves work and, and it just nothing happened. And it wasn't until I fell on this simple idea, okay, of the idea of just there being force in the universe. All right, so we could just draw the force bits as little tiny things. And electrons and protons, and because they're the major players, so as I did my research, it was just quite apparent to me that the only thing in the universe really that does anything important are electrons and protons, and it's obviously the electrons. We'll make them green, and we'll make the protons red. All right. And so the idea is first I just had force bits, and then I tried different numbers and different arrangements and different ways of making them interact, and tried to figure out a way where I can make these things attract each other. But, if I put another electron in here, somehow that would be repulsive. All right, and so the simple rules that I've now come upon that create the working simulation, and create exactly what charge creates, the Maxwell drawing of the idea of a charge with a bunch of radial lines representing the force, and the idea that when it's green and green, they're repulsive. That is, the lines indicate a strength. How many lines you intersect indicates the strength of your repulsion, and if you're opposite, it's attraction. So the simple principle that the simulation is duplicating without any other tricks involved is that if one of these little red bits, so the little bits in the universe are all flying in different directions, zillions and trillions of them. So you can imagine if you were in one spot in the universe, at any one spot, the only thing that are going to hit you are, obviously ones that are going to look like they were heading right for you all the time and blah, blah, blah. And so essentially you're just going to get hit with a bunch of radiation from different places in the universe. And your obligation is going to be to sort of give that stuff back eventually, okay? Unless you're going to get bigger and bigger, you have to sort of give it back. And so you get hit by everywhere in the universe, and then you radiate back to everywhere in the universe, is the simple principle. So that's what these force bits represent. They're just bits of energy moving the speed of light, a little bit of momentum. And the idea is if an opposite one, a proton force, there's an equal number of electrons and protons in the universe, equal number of red and green force bits, let's say. These things are the same size, but this one has a bigger mass. Okay, so I don't know, we just represent that with X, who cares? But anyway, so if the proton force hits an electron, what it does is it just passes through. And the catch will be is that in the process of interacting with the electron, it is changed into an electron bit. Okay, so now it's an electron bit in the universe. So the red bits are inert to the electrons, and the green bits, okay, are inert to the protons. They just pass right through. So just with that feature, you could sort of understand that protons and electrons would end up attracting each other because all of the force that's red, well, I should explain how the red force works. So, but if a similar force, a red force hits a proton, for example, if the proton isn't currently moving, then it just sticks and it shares its momentum with the proton and causes the proton to gain a velocity, and it just stays there until the counter force that Newton would talk about, until a counter force shows up, okay, and hits it from the opposite with a portion of its momentum in the opposite direction, and then both of those bits will reflect back out into the universe and it'll stop again. And obviously if it has more stuff hitting it in one direction, then it will collect numerous bits of force and gain more and more momentum. And if something comes this way and hits it, then it will, this last one will reflect. So whenever there's a reflection, there's two reflections. The reflection going forward that reduces your velocity, and then because you're going to reflect a little bit backward. So that's the simple principle. So when the same color stuff hits you, it gives you momentum. It changes your momentum, let's just put it that way. It causes an acceleration of the matter or a deceleration of the matter, whatever the case would be, and that will be proportional. Like I said, all the energy has to be given back. Nothing is lost or destroyed. So while the little bits are pushing, they're essentially going slower than the speed of light, right? So the little bits go the speed of light. If nothing touches them, one would be from here to here. But if it hits a piece of matter, it moves the matter much slower, so it goes a lot less distance in the same amount of time, which essentially is a degrade in its velocity and therefore its energy in the universe. And I would argue that accounts for the differential caused by gravity. The gravity is just a symptom of moving electrons and protons. To move electrons and protons, you have to occupy force pushing matter. While the force is pushing the matter, it loses a little energy, essentially, if not explicitly. And that is the deficit that you see coming out of the Earth. So the Earth takes in energy, it moves the matter, heats it, and through that process, less energy leaves than went in, essentially, because less speed. The force has lost some of its speed, and less speed means less action in the rest of the universe. All right, so the side effect of figuring out this charge model was it provided an explanation for gravity, which was really quite convenient. All right, so those are the simple rules, and you could sort of understand from those simple rules that if everything red over here, for example, that was heading this way, is going through an electron, well then it's turning into green, which means it's going to be inert to the proton, and it'll go through the proton and come out red again. And you could understand if there was another green here, that it would just do the same thing and it wouldn't affect any of these particles. None of them would get any momentum. So this side of the universe could be pushing something and this side could not be pushing. And then when it's trapped in between, like this relationship, the deuteron, as physics calls it apparently, I mean, not that I've read any explicit references to deuterons, but whatever. You know, it puts this proton in a nomad's land where it doesn't move in either direction directly from the universe, because any energy that's red coming this way is converted by this electron, any red coming this way is converted by this electron. So obviously it's in a condition where it never feels any pressure this way or this way, and can only be moved in ways where it is exposed. So that's another feature, that once these things connect to each other inside of a nucleus, you could understand there'd be all kinds of elements inside that are essentially in this peaceful vacuum of disturbance, where they have limited capacity to be affected by the outside world. When you put 100 of these things or so together. Anyway, didn't want to really get into the more complex elements. Your more complex arrangements. But the simple, you could understand why these would be attractive, is that half the energy that would be pushing on this object can't get to the object. And so therefore these two would attract each other because all the green force can't get through the proton. Let's just get rid of this for now. Just confuse things. So you can understand that any green force coming this way can't get to the electron, and any red force going this way can't get to the proton, and these two will just zoom right into each other. Now, if there's an electron and an electron, no such conversion is going to take place, and any energy that gets trapped between them, like say they're at a distance and they move closer to each other, you could sort of understand that that piece would bounce and be reflected. So any motion by either one of these electrons towards each other would mean that that reflection goes right back to this electron. And if this electron was heading towards this electron, if they both had momentum towards each other, that the bit would bounce back and forth between them and essentially annihilate these arrows. This momentum would get reflected this way, and they would eventually start moving away from each other. So it would certainly create the stopping motion, and then there would be all kinds of mechanisms through which they would gain the capacity to reflect each other. But you could understand that any red bit that passes through going this way, through the electron, gets converted into a green bit. The green bit will hit the other electron and cause it to reflect. So you can understand that all the red energy coming this way and this way is going to be converted into repulsive energy between the electrons, that is momentum in the opposite directions. So clearly there'd be a clear and easy mechanism creating repulsion. So with just this simple stuff, two kinds of matter, two kinds of force bit, and just two basic interactions, the reflection, okay, you could argue it gives it momentum or it reflects. I mean, eventually it's going to reflect. And it's just after it gave it momentum. So there'll be a period of time where it gives it momentum. But you could just understand that the real event is going to be a reflection. That is, well, it's the absorption too. So, I mean, frankly, there's three interactions, okay? There's the green bit that sticks, and then there's the action that takes place when a counter force hits and both reflect back, so you could call that two. And then there's this other interaction where the opposite force changes color, and that's all you need, in my opinion, to run the entire universe. So the entire universe is really just about the attraction between opposite charges and the repulsion between same charges, and that's all that you need to understand the building of a nucleus and an atom, and then the construction of the atom, with the conditional that why are the protons inside the nucleus? And the argument would be is that it just happens to be that these are more massive. Same size. Size decides charge. So they have the same charge. So they have to be the same size, but they're different masses. And so the protons are harder to move. When a force bit's hit, it goes much slower than when a force bit hits an electron. So the protons end up in the more stable nucleus, and that ends up a net positive. And the counterbalancing electrons end up on the outside. So you end up with something close to a balance between the number of electrons and protons. In the bigger atoms it's not so balanced, but you can sort of understand why it doesn't need to be. And so you basically have an excess of protons in the nucleus, and that's because there's no such thing as a neutron. A neutron is just when a proton and an electron become bound to each other. Okay, that object is a net. Okay, neutral in the sense that it has both the positive and the negative element. So it can be called a neutral from a distance, right? It would look, let's just pretend the screen is blue. It would look purple from a distance. It's radiating, this only radiates green and this only radiates red. because of the conversion principle. So it looks just like Maxwell's drawings, right? So if you had Maxwell's drawings in front of you and you recognized the fact that the electron is excreting a force, and it's all one kind of force, and the proton's excreting its force, and it's all just red. Okay, you know. That's a nucleus, but anyway, it doesn't matter for the point. So a neutron is just a composite object. It's just a proton and an electron very close together inside of a nucleus. That's why the nucleus is so compact, it's so small, is because once they're attracted and bound, you know, they become kind of an entity that's a little bit hard to pull apart. So it's not until it gets back into the regular universe, okay, that it can be bombarded and in some way broken apart by the heat that would be in some environmental circumstance. Now, they say it takes 15 minutes for a neutron to decay, okay, but that's an average decay rate. And I don't know if it's, you know, how it's measured and what temperature it's measured. But regardless, we'll get into that little more complex argument about how you basically break these, and how this is basically a hydrogen atom when you do. So when you take it out of the low pressure environment of the nucleus, you know, it looks like it would be high pressure, but it's actually low pressure because of this being stuck in between, being surrounded by objects that deflect the energy. So you could sort of understand that the nucleus is a net positive, so it means there's there's almost twice as many protons than there are electrons in the nucleus. So the electrons are likely the ones in the middle, and the protons are on the outside, just for clarity. And so there's a bunch of electrons that are in environments where they can't really see the universe, and they're, you know, whatever momentum they have, they can't lose, because there's no mechanism through which they can lose it until they make contact, and then you can say the rules change. Alright, so once you have this, then you can go to the stage of talking about what atoms are, and so I guess I might as well zoom right into that one just to get it done, and then I can respond to any questions or blah blah and such. Okay, so you basically got a neutron, which is not really neutral, it's a dipole. So it's the first dipole. So an electron and proton smashed together is a dipole. So that's the first element to understand, is that you can have a mechanism that creates something that's polar. You know, decidedly one half is something. So looking at it from one point of view, this looks red. From the other point of view, it looks green. All right, and from the sides, it looks like who knows what. Well, these things are inside the atom, and the atom is, as I pointed out, kind of polar in its sense, that it has this center that's positive, and then the outside has these bits of negative. So, but you can understand that it's, again, a perspective issue, right? If I look at the atom from this point of view, it's going to look positive, right? You could sort of understand. It's going to look positive from this point of view. From this point of view, it's going to look negative. From this point of view, it's going to look negative again here, positive here. So you can understand that you basically have an atom, and the atom won't have just one polarity. Like, it won't be just north-south. It's going to have a north-south, a north-south, and you know, and then a south-south, and a south-south. So the polarity is going to be in different orientations. It's going to have more than one orientation of polarity. So you could just draw that, I guess, in this way or something. You know, where it's, you know, north south this way, and it's, well, and it's north south. You could be seeing this way. You know, it just depends on how you look at it. Depends on what you're going to see. And you can sort of understand that if I put an electron at different distances from the proton, I'm not going to be able to see the proton, so, or the nucleus. So if the nucleus has an electron in front of it, and the electron is there, right, you can't see the proton. All right, you can't see me. And if it's here, you can see a lot of me and very little electron. So depending on where you are and where the electron is relative to the proton, you will see, okay, a different color. You'll see either the electron's force because it's closer to you, or you'll see the proton because it's bigger. So perspective becomes kind of important. So from a distance, you could be looking at an atom and saying, it's positive, I'm attracted to it, I'll move towards it. But as you get closer, the electron's pressure shows up and says, no, you can't, okay? So you're pulled in, and then you're forced away. And the only way you can bond with that atom or get any closer is that the atom has to turn to the position where it is attractive and there's no electron in the way. So that kind of thing. So that's why it's tricky bonding atoms. That's why you need to heat things and move things, is because you have to smash through that repulsive pressure that can show up because all the atoms have electrons around them, and theoretically all the atoms have a barrier. But the barrier has huge holes in it. Alright, so can have huge holes in it. Alright, so the idea is, so we'll talk a little bit of electricity and magnetism. And I guess I could erase again. Because you don't. So let's just understand that atoms have shapes, and the shapes are dictated by distances between. So in this simple drawing, I'm just saying, okay, we know that the electrons repel each other, right? And we know that the proton and the electron attract. So you can understand from this simple diagram that there is geometry. You know, there's only 100 basic elements where the nucleuses hold together. So there's strict geometry rules about how you place these electrons. So conventional physics has it all messed up. They have them circling and orbiting. They're not doing any of that stuff. When an atom shares an electron, it literally is sharing it. Okay, this atom over here, this nucleus, and could be, they're both using this electron as part of their system of balanced pressure. So you can understand that they literally share the electron in a position. It's not orbiting and doing all this wacky crap. It's stuck in this position here. And the trick is that, yes, if you move this electron, right, it's attracted to the positive. If you move it in, you could sort of understand that that moves it closer to these other electrons, and they'll be pushing it away. So there's a balance of pressure between the attraction to the nucleus and the repulsion of the electrons from each other. And again, you have to understand that the nucleus isn't purely positive. It has electrons also on the surface. And so that's the catch, is that there's no free ride into this net positive, because there are only certain places you can get into the net positive. And the only place these electrons will be is right in those places. That would be, right, so the geometry is going to be that the electrons are always going to be one spaced the furthest away from each other as possible, and still maintain the geometry. So you can understand they end up going in places where there's the furthest distance between the electrons. So that's the geometric rule. So the electrons are in a balanced circumstance. Like I said, it can't really go in for two reasons. One, it's going to create more pressure between these electrons. And two, the nucleus itself already has these electrons in positions that mean it's pretty much guaranteed you have to plow right through the electron to go further in. So you end up getting too close to an inner electron, you know, in the rings of the electrons. So you're always kind of stuck, because wherever you are, there's going to be an electron in your way to getting to the positive nucleus. But the positive nucleus is still very attractive, so you still want to go there, and it's just the other electrons that are stopping you from going further in. Alright, so anyway, atoms have a shape is the bottom line. These electrons can be at different positions, distances, and you can perturbate them, you can push them, okay, and they'll push back out again. They're very elastic in their positions. Alright, so once you have that, then I can do a more basic drawing of a surface and say, you know, in some general way that you could understand that a surface would be connected atoms. You know, they're bound to each other, and so there's a bunch of connected atoms, okay, with electrons on the outside, and a profile that's basically dictated by their shape, you could argue, right? So they have a positive in here, a nucleus. All right. And so you could I could kind of argue that a simple way to metaphor what takes place in, say, electricity is that what happens is these atoms are balanced. Okay, let's say in their balanced state, they're nice and round. And when you push electricity in, what you're doing is pushing on the electron here. That electron pushes on these electrons and expands them, and so you essentially just change the shape of the atom. And now you've changed its polarity in the sense that you've taken an atom that was more neutral in the purple, okay, a mixture, and now you've created one that's decidedly more negative here. So this would be more of a north pole that you would be experiencing here, and more of a south pole you would be experiencing here. So as you push the electrons, you change the shape of the atoms as you push the pressure through. So, and that it's kind of, the pressure moves like a voltage. It moves one bit at a time in the sense that each atom is in a different condition. So say if this one's wrong color. Not that that's terribly important at this stage, but just for continuity's sake. So this one's round here, right? It would essentially share the pressure. So if this one was at 10 pressure, we'd just give it a number, so that's how much stretch it has. And this one's at 0, then this one would go to 5 pressure, and this one would go to 5. So this one would get rounder, and this one would get more oblong, and then it would just move through all the atoms that way. The pressure just migrates, and then it's 10 to, say this one went up to an 8, and then it's, they just keep balancing the amount of pressure. So the pressure moves through the atoms as they all try to balance with each other. They all want to be at the same state because they're all connected by these binding electrons are connecting them. And the binding electrons are basically dictating that whatever pressure this atom's under, this atom has to be under it eventually. So they all want to be at the same pressure. So if I put pressure in one side, they're going to want to be all the same pressure. So the pressure is going to move through all of them. It's all going to be shared. And so if you have you have a 10 in here, and then you're going to divide it into all these atoms, it's going to end up being a 2, when it's done, that kind of thing. A 2 pressure shared by all of them. But if you keep pumping the pressure in at 10, then all of them will eventually turn to a 10. All right, and that creates the positive and negative that you end up in a wire where, you have the positive number of electrons here, the extra pressure of electrons, and then you have the less pressure on the other end. And if there isn't something continually eating that pressure, pulling the electrons, taking them, accepting them, then you'll have a flow of electricity. And if there's there's no ground, there's no place for the electrons to go, then you'll just charge the wire. All right, so through this charging process, you're basically moving electrons in the atom. So again, you could just draw the atom. All right, nucleus in the center. Okay, and so all you're doing is really moving an electron from, say, here to here. All right, so you're moving electrons. And when you move the electron, what are you doing? Well, in the big universe, right, you're in this whole field of energy. And so if you move, what you're going to do is push everything, because you're going to now reflect the universe from a different position. You're moving into a field of energy that might be spaced at this frequency. So that could be a photon, a frequency. And you're going to push an electron into it. And now you're going to reflect this energy at a higher frequency. The energy is going to leave the electron much closer, smaller frequency, because you pushed into it. And you hit this sooner, you hit this sooner, you hit this sooner, you compacted it. So you took energy that was spread over this distance and you confined it to this distance. Because the electron moved into the field of energy and it compressed it. Okay, so I just had a Ken Wheeler moment. He uses a word for this kind of thing. compressions and rarefactions and all of that kind of stuff. But yes, you're just talking about the energy is basically going to get compressed or expanded in terms of the space it occupies. So if you push in with the electron, you're going to compress force. If you pull back, okay, if you're moving backwards to that field, you're going to expand the reflections. Okay, the reflections now will have greater distance between them because it'll take longer for things to hit my hand and reflect off my hand. I mean, if I could literally move my hand at the speed of light, you would see my hand collect all the photons, and then if I stopped my hand, all the photons would hit you that I collected through that whole time I was compressing the space. And the inverse would happen if my hand was going backwards at the speed of light. You'd never see my hand. It'd become invisible, like it didn't exist at all, because nothing would reflect off of it. Nothing could catch up to it to reflect off of it. So anyway, so that accounts for the frequencies created that we call the electromagnetic spectrum, or photons. This is what a photon is. Alright, it gets a little more complicated because photons have polarity. Alright, so the argument would be is that each atom, when the electron moves, it just creates one place of compression. So it's a bunch of little bits in an area, okay, and then another atom does it and it shoots out a bit, a compressed area. And, well, I really should write the compression in the right direction, so sorry about that. Alright, so this one compresses some little bits, and then this atom compresses some little bits, and then this, as they change their shape to account for the voltage moving through the sequence of atoms, they're changing their shape, they're pushing and relaxing, okay, and so they're creating these compressions of frequency in the field, and pushing electron force closer together and then further apart. So this accounts for the idea of polarization, because it's really, the photon doesn't just hit one atom on a surface. It doesn't hit just one electron. The photon, which is the pattern, has to hit in a sequence. So the idea would be is that photons really are individual elements moving in parallel at different heights, so to speak. So this would be the polarization of the atom. I mean, of the what's called polarization of the photon. So which way, there's bits moving this way, bits here, bits here. There are these levels, and these levels have this dimension, and that's the polarization. So this distance is equivalent to the wavelength, and you could argue that that would mean it's 1,000 atoms of separation between this bit and this bit. Could be more than 1,000 atoms worth of separation. So a photon is hitting a surface. What it's really doing is it's hitting one of these atoms with a bit of energy. That's this first bit, right? The first one in the sequence. The first one hits this atom. What's it do? It does the opposite of this. It hits the electron in, expands the atom this way and this way, which is causing movement in these other electrons. And then the next bit arrives, and it hits this electron, not the original electron. It hits this other electron that's moving away because of the initial splash. So the initial splash hits with a 10 power, let's say, and it gives 2 momentums to this one. Now this one gets hit by another bit. It gets a full 10, and now it's a 10 plus 2, so it's 12 bits of momentum. We'll move on to the next electron. The next electron starts off with 4 because it had 12, and now you hit it with a full 10, and now it has 14. And let's say 14 is enough pressure for the electron to be liberated from the atom. So now it's a free electron. Okay, you've ionized the atom because this is the ionizing pressure, 14. Each one of these force bits only has 10. You need 14 to get out of the atom. So that's why it takes more than one of these elements of a photon. So the photon is made out of these energy quanta. Okay, and the energy quanta, it's pretty consistent with what Einstein said, creates the pattern that is a photon. A photon is a pattern hitting a surface. So you could sort of understand it. If I dropped some water, I'd get a ring in the water, And then you could understand that I could drop another thing right there on that ring, and I could increase the momentum of that ring because it's already moving this way, and I'm going to give it even more momentum this way and create a new ring here. And then I could do it one more time out here, and I give even more momentum to that wave, so to speak, if you want to think in wave mechanics. Wow, you really can't see that. Can't really fix that, I don't think. Well, anyway, you saw enough of it. You're just really just adding energy sequentially, okay? So all of this other stuff happened as momentum, going in all these directions, but it's not enough momentum to cause the expulsion of the electron, which is necessary to moving the electrons through the substance. So anyway, so that's how photons can be connected to electricity, is they're basically duplicating electricity in the sense that they're deforming the atoms, changing their shape, so to speak, and by doing that they're basically creating exactly what electricity does, which changes the shapes of electrons. And so if you change the shape of electrons with electricity, you can create light, and vice versa. If you hit the metal with light, you can create electricity. So that connects those two things pretty clearly, I think. Pretty, not complete, but surely is a proof of theory in the sense that it certainly works as a mechanical system explaining the connection between photons and electricity. And then the last one would just be the magnetic one. Okay, and so you're doing the same thing in the sense that you're recognizing that atoms have a polarity. And so I can draw the atom as a shape. All right, and again, the nucleus. And now we can change this. We can understand that from this direction it's positive, from this direction it's positive, from this direction it's negative, north. So now we'll just call north and south, okay? Instead of positive and negative, we'll just say that this is north, and this is north, and this is south, and this is south. And all you're really saying is in a magnet, you have a bunch of these polarized atoms. Okay, either mechanically you have forced them to become magnetic, or they are stuck in this condition. They're stuck in this polar condition where they're connected to each other in this orientation, where the north would be connected to, so this orientation would be connected to another atom in this orientation, right? Connecting the south here, okay, the south end here to the north end here. All right, and you have a south end here and a north end here and a north end here, and you're just doing that throughout the whole structure. So you're creating a whole structure of connected little magnets, but they aren't just dipoles. There's not that they have just 2 poles. They can have 4 poles or 6 poles. So like an iron atom, a few nickel, different substances. The idea is that they have more than one pole to the atom, in the sense that they are distorted in more than one dimension. So they have a pole in this dimension and a pole in this dimension. Well, anyway, you build all of this up into an object that's basically just made out of mini magnets. And so what would you see, okay, if you made such a world where you have all these semi-complex magnetic objects? I don't know what the perfect geometry to draw it in is, but you could just understand that you're basically just saying you're gonna view these connected mechanisms from a distance, and the idea is what you're going to see is the green things are all radiating the green force, right? The polar ends. All right, and the reds are radiating mostly red, all right, and then the greens radiating mostly green. So you can sort of understand that as you build this up, this side's going to be red, this side will have to be green, okay? You can understand that these other sides will be a mixture, and these are going to be connected, red, green, red, green, red, green, and so you're going to have a mixed pattern. It's going to be a little bit of green on this side, a little bit of green on that side. So I would compare it to viewing something like a bullseye. The bullseye can be green in the middle, and then red, and then green, right? Or it could be the exact opposite, where it could start red in the middle and then be green and then be red. And so you can understand that if the appearance of something is like that, then that would be the difference between what the north pole of the magnet is sending and what the south pole is sending as a signal, and what the outside world sees. And so another magnet will see that polar difference, and it will create the attraction and repulsion connected to the fact that it's seeing electron force and it's seeing proton force in these positions. And if they match, then they'll be attracted, and if they don't match, then they'll be repelled. And so the magnetic signal is just another pattern. So like the photon just being a pattern of energy bits at a frequency, the magnetic pattern is just another variation of that, in the sense that it's a more complex pattern, and only other dipoles can see it. Only other things that can be hit with the force in different places compatibly, you have to match the pattern essentially. So other magnetic objects can see the magnetism, where regular objects can't, because they can't match the patterns. So a magnet doesn't produce any energy. The magnet is just sitting there. Okay, I could draw a more simple bar magnet, and basically the idea is this side has a dominance of protons being visible. This one has the dominance of the electrons being visible, because of the geometry. And so one side is radiating the green force and one side is radiating primarily the red force. But again, it's more about this pattern idea. It's really the same amount of force. It's just the mixture is red dominated on one side and green dominated on the other side. So you could say dominating, recessive and dominant, and they just have the opposite circumstance. And so all they're going to do is the same thing. They interact with, say, a wire or a piece of metal. They're going to do the same thing, where they're going to induce, through the pressure they're creating, the compression and expansion of the atoms. And so again, they're going to do the same thing, where they're going to force the atoms to be misshapen. The atoms are going to want to become all the same pressure. So the magnet is essentially going to induce electricity, just like a photon could. And so the magnets aren't doing anything. They're not making anything. They're just taking the mixed world that comes in, the red and green, the red and green, the red and green, and they're basically segregating it. They're saying, I'm going to make the red and green into a specific kind of pattern that I'm going to reflect. So like I said, it's not as explicit as taking, let's say it was red and purple, red and blue. It's not as simple as just taking purple and segregating it into red and blue, but it's the nature of it is that simple, in the sense that the patterns are inverse, and the inverse patterns mean that you can see the difference if you have the polar condition to see the difference. All right. Yeah, so I think that connects all of the stuff I need to connect. So we'll call that just some background that I haven't done in a while. So this subject is much more than the kinetic energy theory. As you can see, the kinetic energy theory really isn't even a part of any of this. I don't need it for the substance of the unifying theory that I'm really supporting and defending. But it just is a perfect example of how the conventional model is under-evidenced, and it can be understood to be a contradiction and nonsensical. Again, they say conservation of momentum, and overtly that means anytime I make exchanges between uneven masses, I either have to destroy energy or I have to create free energy. So, their theory doesn't make any sense. It's not well organized. It's not structured. It's not mechanical. It's full of a bunch of woo particles and woo mechanisms, and and you can understand it as being just a universe full of force that has all the motion, and matter, which just gets pushed by the forces. The forces tell the matter what to do, and the positions of the matter dictate where the forces are going to go. So the forces are affected by the matter, and the matter is affected by the forces, but the matter doesn't affect matter, and force doesn't affect force. So I think that's good enough. So says I. I didn't want to do that. I'm going to move this little bastard. Alright, let's see if there's any... Oof, just a one comment. Not too good, but we'll see if we can sustain anything out of it. Let's see. It's a Saturday night here, and I am listening to physics. Okay. I have lots of questions, but I am relearning this subject after 30 years, so I will keep my naive questions till later. Well, it's not likely to get answered if they're too late, because I'm not going to hang around and talk to the wind. Yeah, I'm not going to bother doing that. So, yeah, I really don't think I have to add much. I guess I'll put the simulation on in the background. What the hell? That would require this to be on, I think. Oh, cool. It put it in the wrong window? No. Okay, this is behind that. I get it. Okay. Well, that's okay. I'll just move this up, because there isn't many comments anyway. Aren't any, really. And you can see them as they come in, if any do. So anyway, so those simple rules are what's making that simulation happen, and it'll do that every time. They'll just basically, it goes from electrons and protons in free space, and it makes neutrons essentially. And once you make the neutrons, then you just have to have some sort of dynamics for them sticking to each other and blah blah blah. So I haven't gotten all of that finished yet. I mean, I have the rules, I just haven't gotten it built into the simulation yet. But a bit at a time. I don't know if there's any feature that's particularly interesting. Let's see if we can change something a little bit. You know, different things you can do to manipulate it. So I think this will... that one's not going to be terribly useful. That one's not terribly useful. I want the one where it turns them there. So all the ones that are being changed in their color are now leaving white. So that sort of gives you an idea that the blue thing is just radiating blue. So anything that hits it, red and blue is hitting it, and it only reflects blue all the time. And the red thing is only reflecting red, but you can't always see that. But that's basically, you know, clearly, if the force was more dense, which, you know, it'll have to be in the future, you could get the idea, you know, that there would be as much stuff being changed in its color as there is stuff in the universe, you know, because of the proximity of the electrons and protons. So from the blue thing's perspective, yeah, it's a little... I'm just trying to think of what percentages of the universe would be affected by density. So I'll think about that on some other occasion, but that's a little complicated. But anyway, so there's lots of little things I can do with the simulation, so eventually it'll be quite interesting. And you can change different things, like how the size of the objects, like I said, size I don't think it ever really... As a practical matter, I think electrons and protons have to have the same size, unless you want to say there's an uneven amount of force or something, because they do have the same charge. The strength of the repulsion is equal. So protons repel each other with the same amount of intensity that electrons do, and vice versa. The north pole of a magnet is just as powerful as the south pole, kind of thing. So the charges would have to be the same. Size would have to be the same, because size is basically saying how much of the universe are you affecting. How many of those little force bits per second are you interacting with? And so what really has to be different about the electron and proton is the density. The protons have more density, and therefore move slower, and therefore get trapped in nucleuses. and such. Alright, well, I can see what the audience is, and then I'll say whether it's no point or a point. Let's see. 9. Well, 9 isn't that bad. You think somebody would have something to say. Okay. I mean, it's bad, but I mean, it isn't that bad. So, 2-minute warning or whatever. If no one's got anything to say, then we'll just call it a video. And such. I can do a refresh, I guess. We'll see what it does. So you can see the electrons, I mean these two protons got too close to each other, but then the force kicks in and pushes them apart, and all that'll happen much quicker when all of this gets balanced to the number of force bits and the speed of the matter bits and all of that stuff. So I haven't really done all the balancing of all of that crap. Let's see, that's all that fits in the screen there. Yeah, well, can't do much about that. Alrighty then, I guess there's nobody about, so we'll call it a morning and move on and such. So let's see, I have to hit this and then I did this. Alright, so till the next time, and so there was something somebody snuck in with. Yeah, thanks for the stream. Well, that's not very useful. Okay. Alright, till the next time and such.